This is going to be a lecture about information. Now, really, this is sort of a taste of something called information theory, which is a really exciting topic, but I don't have time to talk about it in much detail in this course. We need to know a bit, though, about information theory because we want to understand how much data truly is stored inside these sequences of symbols we keep working with. If I send you a sequence of symbols, so here is a sequence of 5 symbols, then sure, I can say I'm choosing to represent this in 8 bits or 7 bits per symbol or whatever, and obviously if I do that, I'm sending you some amount of data. I'm sending you some number of bits. But on the other hand, we do want to ask the question, how much real information is stored? What is the minimum number of bits I can expect to use, at least under certain assumptions? And also to consider the fact that if I look at other sequences of 5 symbols, like this one, it does feel a little bit like there's a little bit less actual information in this sequence than there is in this one, for some reason. Maybe just my intuition, but it feels like I'm learning more from this sequence, and therefore I wouldn't be very surprised if it turned out that this sequence took a few more bits to store on average than this one. So we want some formal way of thinking about that. What we really want, what we failed to achieve in lecture number 2, is to have some formal lower bound, some formal statement we can make about this data cannot be compressed, or this data can always be compressed, or this data can be compressed but only to, 10 bits in total size. Having a lower bound like that is great because it means if we ever are able to achieve that lower bound, we know that our job is over. Now, it turns out we really can't develop a full-scale lower bound that we can apply in general, but there are some techniques from information theory that'll help us out a lot if we can make certain assumptions about our data. For example, if I can assume that each symbol is independent of all the other symbols, which actually, as we'll see, isn't always the case in practice, or actually is almost never the case in practice, but if we can make that assumption, we can in fact state a lower bound on the compressed size. So we're going to talk a little bit about information theory. But in the context of this course, we really think about the study of information mostly, I think intuitively, as whether a given piece of data is interesting or not, with the idea that less interesting pieces of data, less surprising pieces of data, are probably easier to compress. And let me spend a few slides justifying that. Okay, so it's the end of April here in Victoria, and every now and then I run into people at conferences or whatever, and they make small talk, and they say, "How are things going in Victoria, Bill?" And not to put too fine a point on it, but I didn't really get into computer science because of my skill at making small talk with human beings. And so what do I say? Oh, well, it's Victoria, so it's looking pretty sunny outside because it's April. That's not interesting. They would know that. If they know anything about Victoria on the west coast of British Columbia, they know it's pretty nice in April. I could tell them, oh, well, I had COVID last month. That was not very much, that's not interesting either. Not just because that's sort of a downer, but also because, unfortunately, in 2023, people get COVID pretty often. So there's nothing too exciting about that piece of information. It's also a little bit morose. I could say, hey, I just did my taxes. No, that's also not interesting. That's boring. I really can do better than that. Even if my life is boring, I've done more interesting things than that. But really, the reason these 3 points are not interesting isn't so much because they're tedious and because I'm not good at making small talk, although that contributes to it. It's because these are things that somebody listening to me probably could predict to a reasonable extent. That is, they probably know it's sunny outside because it's April. Although they can't necessarily guess that I had COVID last month, it's not too surprising because a lot of people have had COVID lately. And the fact that I just finished my taxes, well, that's not surprising at all because everybody does their taxes in April in Canada, and I think also in the United States. Now, if I were to tell them that aliens invaded from outer space, that would be interesting because that is something that they weren't expecting to happen, I guess, at least not in this part of the world or whatever. And it turns out that actually distinguishing a piece of information not from whether it's, tedious small talk versus not, but from whether it surprises the listener, whether maybe they learn something new from it, that's actually pretty important. Okay, well, there we go. There's my discussion of my boring life. I hope these videos aren't getting too, long-winded with all of my digressions. Anyway, let's talk about volcanoes for a minute. So here is a picture of a seismic monitoring station on the slope of Mount St. Helens. Now, Mount St. Helens is in Washington State. So I'm recording this video right now from Victoria on the west coast of British Columbia, and most of you watching this, that is where you are too. And south of Victoria is the United States, particularly Washington State, which is immediately to the south. And in Washington State, there is a volcano called Mount St. Helens. And there's a reason there are all these monitoring stations on Mount St. Helens. That is because Mount St. Helens is an active volcano. Now, the most recent big eruption happened in 1980. So here's what the mountain looked like before that huge eruption. A nice looking mountain. I could go on a nice hike on the side of that mountain if I weren't so terrified about the whole volcano thing. Early in 1980, an increase in seismic and volcanic activity was noticed. So I imagine it's the case that with active volcanoes, you're always keeping an eye on it, but maybe a little bit of activity isn't too worrying. But there was this escalation in early 1980. And frankly, if I lived near a volcano and I begin seeing that, I would begin to get a little bit worried. And then on May 18th, 1980, almost exactly 43 years ago, as of today, April 30th of 2023, a huge eruption occurred, and it was so massive and the pressure was so massive that it actually blew off the top of the mountain, pretty much. So it destroyed a massive section of the mountain. It shortened the mountain, but also generated this massive amount of volcanic ash, and it spewed that into the atmosphere, and then that ended up blowing around to surrounding areas. There were also landslides that affected areas nearby. So huge amounts of land that were displaced by this eruption ended up turning into landslides that covered farmland and communities that were below it. So it was a pretty big disaster. It turns out that the ash, which blew through the air, ended up settling all over the place nearby. So this photo here, and just by the way, in May in Washington State on the west coast, you can bet that that's not snow. That is in fact a blanket of volcanic ash. That was taken 300 kilometers away from the volcano. Now, Victoria, where I am right now, is only 260 kilometers away, and so there actually was ash seen in Victoria. So apparently people in Victoria back then, I wasn't around back then, but people in Victoria woke up to have ash on the ground. They woke up to discover a blanket of ash on the ground. I went looking for photos of that, and I couldn't find any. Or at least I couldn't, if when I made these slides a while back, I found any, I couldn't use them because of licensing issues. The ash was actually found as far away as Edmonton, and you can go take a look at a map if you're wondering how far away Edmonton is from Mount St. Helens. So the ash ended up pretty far away. This volcanic event was a massive deal. And suppose that, you are working on designing these monitoring stations that live on the side of the mountain that are trying to help predict or keep an eye on this volcanic activity. And then actually, finally, here's a photo of the mountain when everything was said and done. So here is the mountain before. So nice looking mountain. It looks sort of mountainy. And then here is the mountain after. And it does look as if this mountain has had sort of a bad time. And the height of the mountain was reduced by almost 400 meters as a result of this eruption. So imagine that you are the person designing an early warning system. Now, the early warning system, maybe you can use some sort of prediction, but maybe you're just running sensors. Maybe you're just keeping an eye. You've got stations positioned all over the mountain, and you're keeping an eye on activity. And I guess for the sake of nostalgia, put yourself in the shoes of somebody designing one of these systems using primitive computing equipment, let's say in the late 1970s. Nowadays, because we have the Internet of Things and lots of sensors that are cheap to obtain, and we've got wireless connectivity, designing monitoring systems is a bit of a different game than it was 43 years ago. But suppose you're designing the monitoring network of maybe 10 or 11 or maybe 100 systems sitting on the side of this mountain, and they have to send a signal back at regular intervals to some base station elsewhere to indicate how things are going. So that way if you're looking at the entire mountain, oh, there might be some weird activity going on over here, but the station over here is still reporting that everything is good. So they might send back a report, I don't know, every 5 minutes, every 10 minutes, at regular intervals. So how about this? Every 5 minutes, each monitoring station sends out a status code. And I guess each code really is just a number. And we've got a variety of different codes. Obviously, we care about the extremes, which is condition 0 is everything's great. There's nothing to worry about. There's no discernible seismic activity or anything else. Obviously, if we're getting code 0, we can relax. There's obviously also the other extreme, which is a disaster is presently occurring. This monitoring station is about to be wiped out because of an eruption that is currently occurring. occurring. But it's good to have some status codes in the middle so that you're not, I don't know, like too caught off guard by number 5 when it shows up. It's useful to know when you see a little bit of seismic activity and then maybe things go back to code 0. Well, then you can relax again. And if you see moderate seismic activity, get a little bit more worried. If you can detect magma flowing underground, that's obviously a little bit terrifying. So we have a bunch of status codes in the middle. And your sensor network, every sensor is sending out one of these codes every 5 minutes, which is being recorded elsewhere or used for some kind of aggregation. My question is, which of these status codes are the least interesting? I mean, it's true, certainly, you can expect that some of them are more common than others, but which ones are the least interesting? If you're watching, if you are observing the sequence of status codes coming back from the stations and you see something like this, 0, 0, 0, 0, 0, and you just keep seeing this change, oh, maybe there's a 1 in there, then back to 0, then 1, then still some zeros. My question is, which code is the most interesting and which are the least? Well, I would say that although this is certainly the most comforting one, like I'd rather see 0 than 5, code 0 is the least interesting because I'm expecting to see that a lot. I see it so often that seeing it again doesn't surprise me. If I've just seen a bunch of zeros and I see another one, then I'm not too surprised. And if I've generally been seeing zeros, not necessarily if I'm in the middle of a run of all zeros, but if I've generally been seeing zeros, so here, I haven't seen a 0 recently, but I've seen a lot of zeros in my life, in that case, I'm not too surprised that I see another one. And then the question is, well, okay, what if we use a different word? Instead of saying least or most interesting, which code contains the most information? That's an important word, and I can go around rattling off mathematical definitions of things all day long. I'm going to do that for most of this lecture. I can do that, but I feel like when we use a word like this, when I begin to define a quantity called information, it's pretty important that we have some intuitive agreement of why I'm calling it that. So which code contains the most information? Intuitively, I think, in the context of this course, because information theory is a whole big thing that I don't have time to talk about. I sort of want to, but I don't have time. In the context of this course, why don't we think about the word information as a quantitative measurement, so more versus less information. Let's try and equate that with the feeling of being surprised or learning something from a piece of data. If you have a piece of data that doesn't teach you very much, so if I'm looking at my status codes and I'm seeing things in the range of 1, 0, maybe a couple of 2s in there, and I see zeros, well, it is true that I learned something from this observation being a 0. I learned that currently the observation isn't 1 or 2. But on the other hand, because I'm sort of expecting most observations to be 0 or 1, I don't learn very much from this observation compared to if I suddenly saw 4. If I saw 4, I would be surprised, and this would change my understanding of the world a lot more than a 0. Not just because maybe I naively assume that the status is always going to be mild and 0 or 1, but also because what I already know about the world implies that zeros are very common. If I look at the, probability distribution or the frequency of each of these codes, the ones that occur at higher frequencies will surprise me less because I've gotten used to seeing them. I'm expecting them. I see this occur more often. I begin to believe this occurs at a higher probability. And so if I see something that I'm not expecting, I'm a bit more surprised by it and I learn more. It alters my understanding of the world more. So I would argue in that case that the status codes that are less common, even if we put the emotional aspect of the fact that these, terrify me, the status codes that are less common contain more information by that intuitive logic of things contain more information if they're more surprising or if they alter your view of the world or your understanding of the state of things more. Now, if we take it a little bit further away from something so emotionally invested, like a volcano erupting and destroying everything or raining ash down upon us, let's just consider the pleasant situation of the weather in Victoria. As I said earlier, I'm not very good at making small talk, so I immediately go to the weather. Consider this hypothetical, but I think pretty realistic set of weather forecasts or observations for early April in Victoria, so in British Columbia. And let's say that we're a website that's producing weather observations, we probably have some set of standard weather conditions that we could emit. And we notice that in early April, it seems like it's generally pretty sunny. And occasionally it's sort of cloudy or overcast. But there are a few weather codes we probably don't see very often in April. So there is a weather code for snow or flurries or a variety of other ones like that. On the West Coast, I've often seen weather forecasts in the late summer for smoke. That's the situation where you wake up one morning and there's a blanket of smoke everywhere from forest fires elsewhere that's blown in, and so the light sort of diffuses strangely and everything looks rather surreal. That's actually a weather condition because it happens so often these days. But of the possible conditions, which one of these possibilities is the least or most surprising? Well, we can understand that there's some benefit to the context, although most of this lecture is actually deliberately avoiding the subject of context. But if we know, based on what we've already seen, observations we already have, regardless of what time of year we think it is, if we've already seen a few sunny days, I probably wouldn't be too surprised if April 8th was sunny. And if it happens that April 8th was partly cloudy, I don't think I'd be very surprised by that either. There's some precedent that, in recent memory, I've seen a few cloudy days. I'm not too surprised if I see another cloudy day. On the other hand, I would argue that if I saw rain, well, that's a bit more surprising, although it's now the end of April in Victoria, and there was a healthy amount of rain on Vancouver Island in the last few weeks. So I would be a bit surprised, but not too surprised. If I saw snow, I'd be very surprised. It's rather unusual to get full-on snow in April in Victoria. Not impossible, but unusual. And thunderstorms and smoke, although also possible, are relatively uncommon too. So the reason this applies to data compression, the reason that we're talking about surprise versus not surprise, or learning something versus not learning something, is it turns out really that that's fundamental to the value of information. If there are certain things that are more mundane than others because they surprise us less, if sunny days are so common that they don't surprise me, then what I'm really saying is the value of this status of a sunny day is relatively low. By the laws of supply and demand, there's a large supply of sunny days, and therefore it's sort of cheap to use the code for a sunny day, which makes sense in compression because if I am trying to compress a bunch of symbols corresponding to weather observations, wouldn't I want to compress the most common symbols into the smallest number of bits? Would I mind if the code for snow ends up being 100 bits long? Well, not really, as long as the code for sun is like 1 or 2 bits. That's a compromise we're already used to making in this course. So this idea of, classifying information by surprising versus not surprising does, I think, map pretty well onto one of our overarching goals, which is to fairly value the different pieces of information that we see. If we consider a set of symbols, the various pieces of information I could send across the wire, then some symbols might be more valuable than others. And I argue that those are probably the rare symbols. The more rare a symbol is, the more bits it's worth. And that makes sense for compression because if a symbol is rare and needs more bits, I'm not going to see it as often, so those extra bits aren't going to cost me as much. So that's my intuitive idea of what the word information means. If I tell you, oh, the volcano's still not erupting, or the weather is still sunny, well, that's not going to surprise you very much. The volcano has been not erupting as of now for about 43 years. If the volcano, by the way, I'm recording this on April 30th, if the volcano erupts between now and when I actually give this lecture in person in mid-May, then I totally called it. But probably the volcano will continue to not erupt. And if I tell you the volcano is still not erupting, that's not going to surprise you. If I tell you suddenly the volcano did erupt, or there was a blizzard in April or May in Victoria, that probably would surprise you. And just for context again, if you're from somewhere else, if you're from Alberta or Ontario, yes, I get it, that there probably is a blizzard happening right now in Alberta. Sorry, I know it's paradise here on the West Coast if you don't like blizzards. So intuitively, when I've got more surprising information, that more surprising news contains more information, and unsurprising events, because they don't add much to our understanding. They're predictable. It changes little about our view of the world. Those contain less information. And so we can actually begin to quantify that more formally. I already used the word probability earlier in this lecture, and indeed that is where I'm going with this. So it turns out that a high probability event, if you know about the probabilities of things, or you can estimate them based on what you already know, so if you've looked at the weather for the last couple of months and you know that generally things seem to be sunny, you could estimate that the probability of a sunny day was something relatively high. So let's say 0.5 or higher. That's a pretty high probability, but we get lots of good weather in April. So if the probability of it being sunny is more than 0.5, then learning that it's sunny doesn't surprise you very much, and therefore is low information. It was something that you could have expected because the probability is so high. The probability that aliens invade Earth, on the other hand, I'd say conservatively is probably about 1% at most. And so if I tell you that aliens invade Earth, then you'd be surprised. That's a high information event because it has low probability, but it did occur. And again, if aliens do turn out to invade the Earth between now and when this lecture is actually given, then I totally called that too. So if we can give probabilities to events, even if that's just an estimate, as we're going to end up doing, we'll derive our probabilities from what we've seen. So if I look at a sequence of data, so here's a sequence of 5 symbols. I could, even though I don't quite know where these symbols are coming from, if I observe some portion of this sequence, like these 5 symbols, I could say the probability of seeing an A is 4 in 5. I could just estimate the probability, with the idea that as time goes by, if I use a large enough sample, I should expect to get pretty good estimates. So even if I don't know the underlying real distribution of where my symbols are coming from, I can probably develop a good enough estimate over time that I can begin thinking about the occurrence of a symbol in a stream of symbols in terms of the probability of a particular event occurring. I want to talk more about that. I want to do a quick aside to talk about something else. This is actually sort of a review question. So the question is, suppose I want to send you a single digit in base 10. So in other words, I want to send you one of 10 possible symbols, the digits 0 through 9. The reason I'm not saying let's just use A, B, C, D, E, the reason I'm insisting on using digits is I think the best way of making the point I want to make is thinking about numerical data. Suppose that I choose to represent all my data in base 10 and not base 2. Suppose I'm not talking about zeros and ones. You should know by now, and of course you're all very progressive, tolerant people, and therefore you'd agree that really base 10 is no worse or better than base 2. All bases are essentially the same. It's a question of which base is most convenient for pragmatic reasons, like what kind of hardware you have. Generally speaking, when you design electronic circuits, off versus on, so 0 versus 1, tends to be an easier sell than having 10 different possibilities. Although there are plenty of historical computers that did actually do everything in base 10. Okay, whatever, well, that's a subject for a different course. My question is, suppose that for some reason I do everything in base 10, and I want to send you one digit in base 10, but unfortunately to send you that one digit, I will need to use binary. How many bits do I need to use? And this is review from probably a first-year course, but let's just go through it. How many bits do I need to represent all the possibilities if I'm sending you one digit in base 10? Well, let's see. I guess there's 10 possibilities, and so I can compute the number of bits using this formula that you probably by now have memorized. So I take the log in base 2 of the number 10, and that comes out to be something weird. That comes out to be, I think, 3.32. But what do I do with that? That's not really a number of bits that I can, what does it mean to have 0.32 of a bit? Oh, right. We remember from a first year course that actually what we do is we take the ceiling, because we know that I either have a bit or I don't. I'm not allowed to have part of a bit. That makes no sense. So in this case, the ceiling of log base 2 of 10 is 4. So canonically, how many bits do you need for a given number of possibilities? Well, it's this formula. You take the number of possibilities, we'll call that n, and then you take the ceiling of the logarithm in base 2 of that. And then you get a nice whole number, which is the number of bits you need to represent it, even if maybe you have more bandwidth than you need. So if I have 4 bits, there are 16 possibilities. But I only have 10 symbols, which means I'm not using all of the possible bit strings. The point I want to make is not so much about that. It's actually mostly getting comfortable with this fractional bit and maybe learning that it's not so useless after all. So I've worded this carefully, but the number of bits needed to represent 10 possibilities is apparently, so with some skepticism, it's apparently this, but we understand that we can't transmit 0.32 of a bit. If I'm just going to send you some bits and when I'm done, you will have that digit, then I have to send you either 3 bits or 4. I can't send you 3.32 bits. So because I have no way of storing a fractional bit, I send you 4 bits. Now, the fact that the number that the log in base 2 of 10 is not equal to 4, it's definitely less than 4, is a sign that we're not using all of the power of those 4 bits. The fact that it's 3.32 means I don't really need all 4 bits, but I have to use them, maybe we'll say for practical reasons. The reason that this is significant is, yes, it's true that if you just want to send a single digit, you have to use 4 bits. You need the ceiling function. You can't just leave this at 3.32. However, I would argue that this 3.32 is a more faithful measurement of how the minimum number of bits, at least sort of notionally, at least in a thought experiment, the minimum number of bits you need to represent 10 possibilities is 3.32. Whether you can ever achieve that minimum in practice is a different question. So let's consider this question. How many bits are needed to represent a pair of digits? So my pair will range from 0, 0 all the way up to 9, 9. I want to represent 2 digits, exactly 2 digits. This is a thought experiment, exactly 2 digits in base 10. Well, there are 100 possibilities. Right? 0, 0 up to 9, 9. So how do I do that? Well, I have 2 options. One, I could stare at this and say, well, 1 digit is 4 bits. So I could send 2 digits in 8 bits. Can I send 2 digits in 8 bits? Absolutely, I can. And you could argue, well, look, if this 4 bits were the true number of bits you need at minimum to represent 10 possibilities, even in a notional sense, then to represent 2 digits, you would need 8 bits. But that's not the way it works. Instead, there are 100 possible 2-digit numbers, so log base 2 of 100 is this. So apparently, in an ideal world where fractional bits exist, I need 6.64 bits to represent 2 digits in base 10. But of course, I can't actually do that, so I take the ceiling, which means I can use 7 bits. Now, that's the point I'm actually trying to make here. Because if I want to represent 2 digits, and I think of this in terms of, oh, the formula for how many bits I need per digit is just the ceiling, well then the formula for 2 digits should be 2 times the formula for 1 digit. So to get the number of bits for 1 digit, I end up with 3.32 rounded up to 4. I multiply that by 2 and I get 8. But notice that when I think of it in terms of the 100 possibilities, I can represent that in 7, and obviously I do. And notice that if I go backwards from that, if I take my 7-bit representation of a 2-digit number, so here's a 2-digit number, if I take my 2-digit number and think, how many bits ended up going into each digit? Well, it actually is fractional. It's 3.5 bits per digit. So it turns out that a fractional number of bits, I think, is a valid measurement. It's just true that, of course, I can't send you 3.5 bits. But if I send you something complicated, an individual piece of it could take up a fractional number of bits because it's taking advantage of sort of agglomerating and aggregating bandwidth together. And then I'm amortizing out those 3.5 bits over 2 digits, and I end up with 7 bits in total. We can actually continue with this. So to represent 3 digits, and there's a typo here, this should be log base 2, of course, of 1,000, then the log comes out to 9.97. And as usual, obviously, I can't represent 0.97 of a bit explicitly, so I round up to 10. But that means with 10 bits, I'm representing 3 digits in base 10, or an average of about 3 and 1/3 bits per digit. Now, there's a couple of other things directions we can go with this that I'm not going to worry about. But one thing I will observe is, hey, that sort of theoretical, like notional ideal world number of bits for 1 digit was about 3.32. Notice, as I want to store more and more digits together, I can't store a single digit in a fractional number of bits. I have to send you a whole number of bits. But if I begin batching up my digits into packages of 2 digits or 3 digits at a time, notice that when I'm done, by the time I get to 3-digit numbers, I am actually representing each digit in almost that minimum. The minimum is apparently 3.32, and I'm representing each digit in 3.33. Now, this doesn't go down uniformly as the number of digits increases, but it does, over time, trend towards that small 3.32 minimum. So my argument is, although it's true that, yes, I can't send a fractional number of bits over the wire, I can still use fractions of a bit as a way of measuring what we're going to end up calling information content, the total amount of actual data contained in a given symbol or the occurrence of a given event. So really this last example, the point of this last example was to try and build a little bit of comfort with the idea that a fractional number of bits is sort of an intuitive concept. There are reasons it does make sense. It's a generalization of our usual way of measuring things in binary, in bits, but it is, I think, a generalization that we can make. So of course, when I actually send you bits, I send you a whole number, but I can reason about the number of bits needed for a component of what I send you in terms of a fractional number of bits. Now, there even are cases where I could argue that a particular symbol is effectively being sent in, I don't know, 0.25 bits per symbol. So if we consider, and that's again in aggregate, that's by agglomerating a bunch of symbols together and sending them all at once with a clever encoding, I could realize such a savings that the effective amount of space I need per symbol is less than 1 bit. So one way you could achieve that, a way that is actually not so relevant to this lecture, is using RLE. If I have a huge number of characters, so let's do let's send a whole bunch of A's and then a whole bunch of B's. And there are, I don't know, how about 255 of each? So I have 512 possible things. And if I store this with RLE, well, I could store it in a representation. This is just for the sake of visualizing it, but not real RLE notation. But I represent a run of 255 A's and a run of 255 B's. And if we assume that my original input symbols were 8 bits and my runs are also 8 bits, then I am storing a sequence of 510 things in only 32 bits, which means each symbol, each of the original symbols in my sequence is now being stored effectively in less than 1 bit. So even though that seems even less intuitive, the idea that something can take up less than 1 bit of space, that's possible too. And so when we see that later in this lecture, it looks a bit weird in the more formal context we're about to jump into, but maybe this example gives you, I don't know, a good place to put your mind as far as thinking about what the meaning of fractional bits is. All right, so back to our mathematical definitions. I want to define mathematically a quantity called information. Now, this quantity, what I'm going to write as I of A, I'm going to just call it information, so the information of A. There are contexts in courses that aren't this one where we would want to be clear, we mean formally the self-information. The idea behind calling it self-information is if this event A, so notice how I'm not talking about symbols yet, I'm just talking about some event that has a probability of occurring. So it raining tomorrow is an example of a possible event, or aliens invading from outer space. Suppose there is an event that can occur, and it occurs with this probability, P of A. When I refer to the self-information of that event, that is essentially a question of how much data have I given you if I tell you the event A did occur. So if I tell you that the event occurred, how much information have I provided to you? How much have you learned? We call that self-information because it's the information that goes with the event having occurred and nothing else. There's no contextual information provided, just A occurred or A didn't occur. And we define it to be this quantity here. I thought for a long time about ways I could intuitively justify this, but it would end up making the lecture very long. I have a feeling, though, that you'll become comfortable with the formula once we've seen a couple of examples. So this formula is intended to measure information in some units. The idea being that we could choose to represent, if we store data, we could choose to represent it as a stream of symbols in some base 2, base 3, base 5, base 10, whatever. And therefore, we should have a measurement of information that is base agnostic. Now, when we care about specific measurements of specific information, we obviously care about the type of data we're storing. In this course, we are obviously talking about zeros and ones. We're talking about binary, and therefore, this parameter, the base of the logarithm, we will always set that to 2. Because we're going to measure, and that changes the units of the calculation. When I measure information, I'm measuring it in terms of a specific base when I represent data. There are weird names for the units if you use base 10 or other bases. I'm not going to worry about that. You can look that up. It's a weird bit of trivia. But basically what this tells us, if I set the base, the information that I get, this self-information formula, tells me how many digits in that base will I need to represent the information content of this event, with the idea that more common events, less surprising events, are worth less. They should be stored in fewer bits. Whereas rare events, surprising surprising events might be worth more and stored in more. So again, if I keep telling you the volcano is still not erupting, well, all of these zeros can probably be stored in a small number of bits because you're expecting them. You learn very little from them. Whereas this 5 is extremely surprising and therefore worth more and contains more information. So in this course, we're always going to set the base of this logarithm to 2. And that means the output of this formula is going to be in bits. It's going to be measured in bits. So we say, therefore, that I of A, the information of A, or the self-information of A, describes the number of bits of information in event A. And when I say in event A, think about me telling you event A did occur. The process of me transmitting that information to you, how much information have you received? So one example is, suppose that event A occurs with probability 1 over 4, so 0.25. Then the self-information is, well, it's log of 1 over P of A. And notice that there actually are 2 forms of the formula. I can either plug the probability in directly and then negate the log, or I can do this. For fractional probabilities, I sort of like this version here. So the information content is therefore 1 over the probability, which ends up just being log base 2 of 4, which ends up being 2 bits. So this event, if it occurs and you learn of it, you have learned 2 bits of information. And we can take a moment to actually consider that this formula is basically just a generalization of the formula that we're used to from first-year courses for how to compute the number of bits needed to store a given number of possibilities. The issue is this formula allows for the case where certain events have different probabilities than others. So here's one way of connecting the two together. Suppose that we have 4 different events, A, B, C, and D. But each event occurs with the same probability. They are all equally likely. So they each occur with probability 1 over 4. And that means that the information content of A is still going to be 2 bits. And it's also going to equal the information content of B and the information content of C and the information content of D, which is 2 bits. And there are 4 possibilities. When I have 4 equally likely possibilities and I ask, how many bits do I need to represent one of these 4 equally likely possibilities? Well, it's the same as we're used to. It's 2 bits because there are 4 possibilities and you need 2 bits to represent that. Also notice that the number comes out to be a whole number because we were lucky enough for the thing inside the logarithm to actually be a power of 2. The issue is, what if we have a situation where some things are more likely than others? It's true that 4 equally likely things, if they're valued fairly, should all be represented in the same number of bits, because each one is equally likely. But what if there are cases where certain things are more likely than others? So we'll leave A at 1 over 4, but what if C could occur with probability 1/2? And that would mean maybe that B and D occur with probability 1 over 8. Well, if C is more likely, then it's less surprising. And that means that because it's going to happen more often, if I want to represent it in a fair number of bits, I want to use fewer bits for C because it's worth less. Information that's less surprising teaches you less about the world and therefore is worth fewer bits. It's worth less of your time or your energy or your bandwidth. So this formula for self-information is, I think, a natural generalization of the formula that we're already using to compute how many bits we need for things. It's just an adaptation that allows us to vary the number of bits we need based on the value of the information, based on the value of the data. That's still probably a bit nebulous, so let's talk about a sort of thought experiment. Now, this is going to be a tough one because there's a certain thing we, as people that have already learned a bit about compression, want to do with these observations. And we're going to have to resist temptation here. So the issue is, I'll construct this a certain way, but I'm going to keep coming back to this constraint because it is going to twist our mind in knots if we try and apply techniques like run length encoding to this, because we're not going to worry about that for this lecture, and I'll explain why in a minute. So let's consider an experiment where I go and stand on the side of the highway and I watch cars go by. And I count, in this case, 20 cars that go by, and I observe the color of each car. So I've got red, then another red, then blue, then red. So it's a 2-lane highway, so I'm only going to see 1 car go in each direction at a time. Then blue, then red, and so on. So I observe 20 cars, and we make the assumption that each car is independent and identically distributed. So that is, what I am observing here are a sequence of independent events. There is no correlation. Now, what that requires, I think on average, if I stand at the side of a highway, we can sort of assume that. If just down the road they were having a convention of blue car owners or something, that could have some effect because there could be some sequence of all blue in a row. But we'll assume for now in this thought experiment that each car is independent from every other car. So the fact that I just saw a red car doesn't change in any way the probability of the next car being red or blue or whatever. So suppose that I observe 20 cars, and from those observations, so I'm going to write this as probability. This is observed probability. I've observed a sequence of things, and based on that sequence, I have computed an estimate of the probability. I don't know the underlying distribution. I don't know who's putting these cars on the road, but I can estimate the probability based on what I've already seen, as long as I assume that everything's independent and identically distributed. If this is a sequence of independent and identically distributed events, and I observe a bunch of them, then I should be able to estimate the probability of the next event pretty well after a while. My estimate should get better and better. So I have that. I estimate the probability. The reason why the fact that this is an estimate shouldn't bother us too much is what we're going to end up doing with this eventually is using this towards a compression scheme. And in the compression scheme, we also don't care. If you give me a 100 megabyte file, even if each symbol is independent and identically distributed, I don't care that much about the underlying distribution. I care about the observed distribution. If I look at every single symbol in the file, and I have to be careful because that could violate our streaming requirement later, but if I look at every single symbol in the file, I compute the distribution based on what's actually there. So I have that. I've computed the probability of each car. So if I were to make a 21st observation, I could reasonably assume that the probability of the next car being blue is 0.25, and the probability of the next car being red is 0.5. And so I could represent this sequence of things. So I've got 4 possible colors, apparently. I could represent this sequence using 2 bits per symbol. I could just assign, let's do this. Blue is 0, 0, gray is 0, 1, purple is 1, 0, and red is 1, 1. I could do something like that. I have also computed for each type of symbol the self-information. And notice that higher probability events have lower information. So red, the most common type of car, its probability is 1 over 2, which leads us, so of course that means the self-information would be log base 2 of 1 over 2, which is log base 2 of 2, which is equal to 1 bit. So if you see a red car based on this distribution, you have observed 1 bit of information. Now, if you see something rare, like a purple car, apparently you have observed 4.32 bits of information. Now, that fractional part is probably still a bit weird, but as I said, put your mind back in this idea that on average, we can still be talking about fractional numbers of bits. If I transmit a 2-digit number in base 10, each digit could be represented in 3.5 bits on average. So if I see a purple or gray car, I have gained more information, more understanding of the world, because those were rare events than if I just saw a red car. So I could represent these symbols using 2 bits per symbol, but isn't that sort of unfairly valuing certain things? It's overvaluing red. Red is so common, by the laws of supply and demand, it should be cheap. But it isn't. It costs exactly the same amount as purple, something that's rare, something that according to our measurement of information is 4 times more rare than red, or more than 4 times. So consider that. If I just use 2 bits per symbol, I am not fairly valuing each possibility. And so we can think about information, the self-information of a symbol, as a fair value. It might not be an attainable fair value if I choose to encode each symbol in a discrete number of bits. So if I said, well, I'm going to try and encode these in a way that matches up with their value, I may never be able to achieve that. So I could, for example, decide to encode red in 1 bit. I could say red is just going to be the bit 1. If you see the bit 1, you've seen red. If you see blue, we'll do 0, 1. So if you see 0 followed by 1, that's blue. If you see gray, okay, maybe gray can be 0, 0, 1. Well, that's not 2.32 bits because I can't actually encode a single symbol in 2.32 bits. And if you see purple, let's do 0, I guess 0, 0, 0, 1. Perhaps. Okay, that's 4 bits. I might be able to do better than 4 bits, and we'll see that later. But that's close. Notice how this one came in a bit above our optimum, so obviously our optimal number is 2.32. We couldn't do that. This one came in a bit below. I was able to actually do better than 4, maybe because I wasted so much on this. So I can't actually achieve these in all cases, although it turns out later in the course we can achieve them in many cases. I can't achieve these in all cases, but we can view the information content as sort of the ideal fair value of the symbol. If we want to fairly value the symbol based on its probability, this is how many bits we should use to represent it. In data that we represent by 2-bit encodings, if I encode blue as 0, 0, gray as 0, 1, purple as 1, 0, and red as 1, 1, if they all use 2 bits, that is sort of implying they all have the same value, which is in turn implying that they all have the same probability. And so I should only see such an encoding ideally in cases where every symbol occurred with probability 1/4, and that is not happening here. And so, logically, symbols that occur more often should have a shorter bit sequence, not just from the point of view of valuing them fairly. So obviously, red is more common, so it should be cheap, but also red is more common, so I want to use fewer bits because I'm trying to compress. If I want to compress, I want to use as few bits as possible for the most common things. I don't mind using more bits for rare things because hopefully they don't occur often enough for that to waste space. So we can think about it as a fair value. We can also think about it as the number of bits that an ideal representation. So if we were allowed to make whole numbers of bits representations, so 2.32 bits per symbol, an ideal representation of a gray symbol or a purple symbol would be 2.32 bits or 4.32 bits respectively. And so again, what we're emphasizing here, what I'm really driving in over these last few slides is that high probability symbols should have a small number of bits. They should have a number of bits that is as close as possible to their self-information, and because they're so common, they're less surprising and therefore have lower information. And because in this case, the value of each color varies because the probability is different, we need to find some way of first quantifying exactly how much space should I need for this sequence of independent observations. There's 20 observations, so if I use 2 bits per symbol, I can store it in 40. But it feels a little bit like I could, if I value symbols more fairly, because we already, I hope, can agree that if we just use a 2-bit encoding, we are not valuing symbols fairly. So this 2-bit encoding that results in 40 bits is based on unfair valuations. If I use more fair valuations, if I use encodings that align more closely with information content, I should be able to store my symbols in fewer bits. And the question is first, how many bits is that going to be? And also, how do I come up with the encoding? How do I come up with an encoding that does red in 1 bit, blue in 2 bits, and gray in some number of bits as close as possible to 2.32? Those are questions we're going to unpack over this lecture and the next 2 lectures. So I'm going to skip over this because I already talked about this, and this one too. So these are slides that you can take a look at later. And here's the point I was making a minute ago, which is 40 bits if I don't use a fair value, but if I do try and fairly value each symbol, I might be able to do better. I want to eventually have a measurement of that. I want to eventually be able to measure not just what is the fair value of each symbol, but what should I guess if we assume everything is independent, what is the optimal size, the best compressed size I can get if I find a way of representing each symbol in this number of bits. Here's a different sequence. Suppose I stand by the side of the road one day and I see blue followed by 19 red. I never even see any other colors, so I actually only have blue and red in this distribution. The other things occur with probability 0 based on my observed probabilities. So in this case, blue is high value. It is extremely high value because it occurs only once, just like purple in the earlier example. Red is incredibly cheap. So cheap, in fact, that it's worth way less than 1 bit. And as I said earlier, I was trying to vaccinate you against the sort of shock of dealing with these sub-1-bit things. Remember that we've already seen cases in this course where a symbol can be represented by less than 1 bit of data. So although this seems like an odd thing to talk about, that red is 0.07 bits of information, maybe we can find a way of actually achieving that over time, amortized over a long compressed sequence. So in this sequence, we've got red with such a high probability that it's worth almost nothing. And if I try and come up with a bit encoding, I actually don't really have, if I encode each symbol separately, notice how I keep saying that. We don't actually have to encode each symbol separately, but suppose that I do. If I encode each symbol separately into a bunch of bits, I have no way, obviously, of getting this. The best I can do for red is 1 bit, so we'll have red be the bit 1. And I guess blue is now going to be 0 bits. So blue is now at a significant discount. But why not? If I use 4 bits for blue, I'm just wasting space. If I have a way of selling blue for cheap, I might as well do that. So in this case, I could just use 1 bit each. But keep in mind, the discount I'm getting on blue, the fact that blue is represented in way fewer bits than its information, that is only because of the inflation of red. Red is being sold for so much more than it's worth, and in exchange, I can invest in selling blue for cheap. What I want to measure isn't just the information content of a symbol. It is, what if I sample so I have some probability distribution, so let's say it's this one, and I sample that distribution over and over again. Now we can think of this formally as a sequence of samples, like I sit down and make and sample a distribution, or we can say I've already observed a sequence of things, I've computed the observed probability, and I absolutely believe this is a sequence of independent and identically distributed events. Now, of those two criteria, it's independent that's going to cause us trouble, because there are lots of cases, especially in compression, so think about the last lecture, where events aren't independent. If I've already seen one symbol, the probability of the next symbol changes or is dependent in some way. So if I see the letter Q in English, the probability of the letter Q goes way up. And that means that observing English text is not observing independent events, because the previously seen text implies what I'm going to see next. And that works at a meta level too. Dependencies don't have to be consecutive. If I've already seen a certain word in a piece of text, let's think about a book or something, it's very likely that I will see that word again after a while. So consider, for example, if you ever had to look at a transcript of my lecture videos, you would probably agree with this. There are certain, and trust me, people give me a hard time about this all the time already, so please don't do it yourself. There are certain phrases or words that I use over and over again. If you look at the transcript, and you notice, for example, that the phrase "you might notice" appears over and over again, then this phrase, "you might notice," if it appears much later in the transcript, is of lower value. It's less surprising. You are not surprised if you hear me say, "you might notice," because I say that all the time. And I'm going to say it probably before I'm done talking about this slide, because I say it so often. So the issue is that dependencies show up all over the place in data, and they don't necessarily have to show up consecutively. We'll see a few that show up consecutively. As I said, if you want some context for consecutive dependencies, think of Q followed by U in English. It is not true that even if different English letters occur with different probabilities, those probabilities don't remain the same between different characters of text, because in general, a piece of English text is a bunch of events that are correlated to each other. This lecture is talking only about independent sequences of events, where the probability of this character being a red has nothing to do with the characters you've already seen or the ones you're going to see in the future. It is completely independent from all of the other ones. If I have such a sequence, and you might already be thinking, why would I have that? In compression, we're working with patterns and context. How would I have that? Don't worry, I'll talk about that later. If I have such a sequence of independent and identically distributed events, I want to figure out how much information is contained in this entire thing. If I know each symbol has a certain amount of information, I know how many symbols appear in total, I can work out, if I look at 20 observations from this distribution, whether they be this particular set of 20 observations or some other set of 20, how many bits can I expect that to be in terms of total information? That is a quantity that in this course we are going to call entropy. And it's computed in a pretty, I think, obvious way, given the way that I've set it up, given the way it's defined. So we're still talking about random variables and distributions. Let's let x be a random variable over a set of n possible outcomes. And these do not have to be equally likely. This is not a uniform distribution. We're going to define this quantity p sub I to be the probability that x takes on the value I. So outcome I occurs. We then define the entropy of the random variable x to be this. So this definition of entropy is just the word entropy, but this is the definition applied to a random variable. In a minute, I'm going to want to define entropy for a sequence of things. When I define entropy for that, we have to be a little bit more careful. But for now, the entropy of a random variable x is this thing. We usually use h to denote entropy. One thing I will observe here is that this is actually the weighted average of the information content of each of the possible outcomes. If I can expand this summation out a little bit to say, let's see here. So what I can do is if I move the negative sign in one, so I've got the probability of outcome I sum over all possible outcomes. I think there are a couple of typos on this slide, so this should be 0 up to n minus 1 because I'm using zero-based stuff here, because we're all C programmers at heart in this course. I end up with this sum here, so log base 2 of the probability of event I, of outcome I occurring. And I notice this is actually just the information associated with the event that X comes out to be I. So what I've actually done to compute this entropy is just taken a weighted average of the information of each symbol weighted by the probability that that symbol occurs, which does make some sense because each symbol contains some amount of information, but if I want to make an average, I should weight the average by how likely that symbol is to occur. Blue has a large amount of information, but blue doesn't occur very frequently. Red has a small amount and does occur frequently. So entropy in this context is the weighted average of the information content of each outcome, weighted by the probability of that outcome. I also think that this is sort of a typo. Maybe that's obvious because I've actually already defined pi up there. Sorry about that. I'll fix that in the posted version. So the entropy value h gives us the average number of bits of information weighted by the probability of each symbol in a single value of the variable x. Now here's another occasion where you can notice that if I do have a uniform distribution, so if the probability of each outcome is exactly the same, then h is just equal to log base 2 of n. The number of bits in one observation of x is just equal to our formula that we're used to, which makes sense because the formula that we're used to is how do I represent this number of possibilities? Not accounting for the fact that some possibilities are more likely than others. Entropy and self-information give us a way of generalizing that computation to the case where some symbols might occur more often than others. So if we interpret the sequence of observations we have made in this example from earlier as independent samples of a random variable with this distribution in all cases, then the total entropy is 1.68 bits, which means on average, one observation, well, I shouldn't circle that one. If I make a new observation, I know nothing about it, I should expect that this observation that I make will contain 1.68 bits of information. That's the expected number of bits. It might contain more, it might contain less, but the expected number is the entropy, 1.68 bits. But we're not quite done. So I guess we are almost done with this, but the entropy of this ends up being 0.29. Because this has this one extremely common event, that weighted average is affected disproportionately by this. So if I make a new observation, I should expect to receive only 0.29 bits of new information, because odds are, frankly, I'm going to see a red, and red doesn't mean very much to me because I've already seen so many red that I'm not going to be surprised. One other observation, I was getting a bit ahead of myself a minute ago. I do have other points to make. One other observation to make here is this, because this is a sequence of independent events, the ordering of these events makes no difference to this calculation. So we are very tempted probably to look at this observed sequence and with our minds towards compression, think about stuff like, oh, I could use run length encoding. Yeah, maybe you could, but that's not what we're talking about right now. We're talking about taking independent observations, sampling a distribution with replacement. So if I observe this sequence of cars passing, the probabilities are all going to be the same. The blue occurred somewhere else, but the position in the sequence means nothing to us. It's just I do a bunch of observations and count how many times I see a particular car. And so I got a bit ahead of myself. I answered the question too soon. The question is, what does this entropy not tell us? And one thing, a big thing that it doesn't tell us is properties of the data that depend on context inside of the data. So if I've already seen a red, is it maybe more or less likely I'm going to see another red? Not in the model that we're using. In the model that we're using, we assume that each one of these things is completely independent from the others and that we make this observation sort of in a vacuum. That is, maybe we could say we have 20 different people and each person makes one observation and they each take turns making observations. If you're the one making this observation, you know nothing about the other observations that have already been made. And so when I compute the entropy H, what I'm saying is if you're the one making this observation before you've made it, how many bits of information can you expect to receive from the observation? That is the entropy H. So we're still quite a ways away from the properties of actual data that we work with. Actual data tends to contain contextual patterns. So runs of the same character or cases where the probability of a symbol changes depending on the context. That is not yet covered by the model we're working with here. There is a way of applying this definition of entropy, which as of yet only applies to sampling a single random variable. There's a way of applying it to talk about the entropy of a sequence. What I really want is for somebody to tell me, what is assuming that every element of this sequence is an independent observation, how many bits do I need at minimum? So what is the minimum number of bits I need to represent this sequence under those conditions? Or a sequence whose symbols are distributed according to these probabilities. There is a way of generalizing, and we formalize it on this slide. This is almost a restatement of what I've already said, but we need some way of formalizing this because our earlier definition of entropy was based on a single sample of a single random variable. So if I want to talk about the entropy of a sequence, I have to define a different quantity because it turns out the entropy of a sequence can be defined in lots of different ways. What I'm going to define on this slide, I'm going to denote it by h of s for a sequence S. And that means you're going to think this is just the sort of general entropy, but it actually isn't. It's because we're going to use this form of entropy for most of the course. There are actually other versions of entropy we can define for a sequence. This is formally the first order entropy. And you should hear the term first order and think about it like first order approximation. There are higher order forms of entropy that capture more of the character of the sequence. First order entropy you could almost think of as sort of an approximation in many cases. So let S be a sequence of data. So here it is k elements long, and each element of the sequence is some symbol from this alphabet. So formally I had to write this, but each S sub I is going to be one of these things. All right, now let's take the sequence and look at the probability of each symbol occurring. So what I mean here is that if our sequence is over 3 symbols, so we've got A, B, oh, that's an ugly looking B, A, B, C, A. Okay, so the sequence has length 7. What I'm going to do is I would like to use my definition of entropy from earlier. So what I will do is define a probability of each possible symbol. So for example, the probability that I see symbol A will be the number of occurrences of A, that's this quantity here. So we've got that. So wait, the number of occurrences of A is 4 over the number of symbols in total, which is 7. That's it. That's all I'm doing. I'm just counting the number of positions of the sequence that are equal to each symbol and defining the probability of the symbol based on that. So it's the same thing I was doing a few slides ago. These are my observed probabilities. The probability of B is then equal to 1 over 7, and the probability of C is equal to 2 over 7. And so, of course, all the probabilities add together to get 1, and we can then say, using these probability values, let's invent a synthetic random variable called x, which is defined to behave based on those probabilities. The probability that x comes out to be a particular symbol is just whatever probability that I've already gathered from my sequence. So I've taken my sequence, turned it into a probability distribution, and then contrived a random variable based on that. The first order entropy of the sequence, which we're going to call h of s, is now defined to be the entropy of this new random variable we've created. So we take our sequence, turn it into a random variable, and from now on we're just going to assume that we're doing that. This formalism isn't going to be needed, but we need some way of laying this down, and then we call the result the entropy of the sequence. Now there is a difference when we talk about sequences between saying entropy, which is supposed to be a measurement of all of the information in the sequence, even including information that's subject to dependencies, and the first order entropy. The first order entropy is only going to capture the information assuming that all of the symbols are independent from each other. And that isn't an assumption we can always make. So when we talk about first order entropy, we are only capturing the information content under the assumption things are independent. Now, outside of theoretical settings, so after this lecture, I'm going to keep saying entropy in the context of a sequence, and outside of this lecture, when I say entropy with no qualifier, I will mean first order entropy, because we're not going to go into more detail about higher order entropy because of simplifications we're going to see we can make in this course. We're going to see them later in this lecture. If you're a grad student looking for a presentation topic, I think higher order entropy is really interesting, and I think it would make a great presentation topic. So there's this theorem, and again, this theorem, you have to take this with a grain of salt, because if you're not careful about how you read this, it looks as if there are easy ways to violate this theorem. And the key thing is, again, that word independent. So a sequence S of n independent and identically distributed elements, so the distribution is the same for every element, which means we can just derive it once based on our observations, if we have a sequence that meets that criteria, that sequence can be stored in no fewer than this number of bits. So we compute the entropy of the distribution, that's h of s, that is the average number of bits per symbol, and multiply it by the number of symbols. That is the minimum number of bits that it would take to represent the entire sequence. And that's computed based on the entropy. And then this is, of course, the first order entropy. So this is a lower bound. This is saying if you can show me with a sequence of independent events, if you can show me some encoding that puts it into this number of bits, that is the best you can do. You can't do better than that. So if you get that far, you're done. You've achieved compression. It's over. So of course, when you notice that you have this, you think it's time to celebrate. But remember, unless you can be sure your events are independent, this bound doesn't necessarily hold. So there could be ways of getting a better compression result than this if you have a sequence of symbols that have dependencies. That's why you should take this theorem with a grain of salt. The theorem is useful, but outside of contexts where we can be absolutely sure of independence, it doesn't necessarily always apply. And so remember that h of s, the entropy, the first order entropy, gives the average number of bits per element. So if I make one more observation, how many bits should I expect to see in this? And then n times that is the number of, if I multiply the average number of bits by the number of total symbols, that should be the number of bits I need with an ideal encoding to encode the entire sequence, if there is no dependence between elements. So in this case, I've changed sequences here, but in this sequence, which has 16 symbols, and notice that the probability distribution, these probabilities have been truncated, but they're 0.125, so this is 1 over 8. These probabilities have worked out so that the information comes out to whole numbers in all cases. This sequence has an entropy of 1.75 bits. So if I make a new observation, I can expect it to give me 1.75 bits of information. The bound is therefore 28 bits. Now, if I were to encode this sequence using 2 bits per symbol, which is not fair value because the information content of each symbol varies, if I encode this sequence with 2 bits per symbol, there are 16 elements in the sequence, so I should expect this will take up 32 bits. The bound tells me that if I come up with a clever encoding, if I'm able to represent each of my symbols by a number of bits equal to their information content, I could get this sequence down to 28 bits, and that's it. So a sequence with this set of probabilities here, and where everything is independent, could go no lower than 28 bits. Now, there's a separate question of how do I actually come up with such an encoding, but how about this one? Here is a mapping. I have blue be 111, I have gray be 110, purple is going to be 10, and red is going to be 0. If I use this mapping, notice that the length of the encoding always exactly matches the information content. And therefore, apparently, this is an ideal encoding. It fairly values the symbol. If I use this encoding, sure enough, I get 28 bits. I have realized the lower bound. Now, I was lucky because in this case, the information content was a whole number, and therefore I could be expected if I encode each symbol separately, there's that caveat again, if I encode each symbol separately, I actually can find a way of encoding each symbol into a number of bits exactly equal to its information count. I don't always have that luxury. And so I have now achieved optimal compression. 28 bits in this context with independent symbols is optimal. That is something we've been really hoping we'd come up with in this course, and we have, but only for one case where symbols are independent. Now, compared to our normal 2-bit encoding, this would be a compression ratio of 1.14. I mean, we are getting compression. But if we argue that a sequence of independent events, which occur with some probability, is a bit more randomy, I guess, it's more like random data than typical data, like English text, then I guess it's not too much of a surprise that our compression ratio, even with optimal compression, isn't very good. And notice that one of the reasons we get this is because the length of the encoding happens to exactly match the information content of each symbol. So one question we should have is, okay, now we've got a more, I don't know, like a case that's going to occur more often, which is one where the information content isn't a whole number for some symbols. Can we design the same kind of mapping for a sequence like this one? If we again assume that all of the symbols are independent, that events occurred independently. And what about this one? Well, okay, even if we could somehow find a way to do it for this one does not seem likely. How do I represent red in 0.07 bits? That makes no sense. it's because probably your mind is still positioned in a place where you think that you want each symbol to be represented by its own little bit sequence. We'll see later on, in the same vein as representing our digits in base 10 all together as pairs of digits, there are in fact ways of encoding a red symbol in this case in a way that over time, asymptotically I guess, you will see it realized in 0.07 bits per symbol. But then the question is, how do I do that? Where do I get the encoding from? Well, the technique we used earlier, which is separately encoding each symbol, definitely won't work for this situation, because how do I make an encoding that's 0.07 bits long? But even in cases where I can produce some encoding, like this one that I produced a few minutes ago, how do I do that? Where did this come from? Was I just lucky? I mean, I guess in this case, maybe I came up with it by hand, but how do I do that in general? What algorithm do I use? Okay, so that's a question we have to spend a lot of time answering. The next 2 lectures will talk about a way of deriving an optimal encoding in the case where you use a separate bit sequence. So you encode each symbol as a separate sequence of bits. That's going to be something called prefix coding and a specific version of prefix coding called Huffman coding. And in general, though, this idea of coming up with a way of encoding each symbol in a number of bits that approaches this lower bound, that approaches its true information content, techniques for doing this encoding are called entropy coding, whether or not they use a separate bit sequence per symbol. If they are encoding techniques that are designed to reduce each symbol to something that is as close as possible to its true information content, we are performing something called entropy coding. And most modern compression formats, and I mean really all modern compression formats, except for extremely specialized ones, pretty much use entropy coding of some form as the last step in their pipeline. The last step. And it's quite uniform. It's always the last step. All of them do a bunch of other stuff and then entropy coding. And we'll see why over the next few slides. It's basically to do with the fact that all of our logic we've come up with so far, including that lower bound, only applies when things are independent. And usually, if I have my compressor, what goes in is not a sequence of independent symbols. So if the compressor is going to do a bunch of stuff to the data, go through a bunch of stages, often those stages are doing whatever we can to make the set of symbols more independent. Once we have a relatively independent sequence, then we throw it into entropy coding. So there are a few ways we can think about entropy coding. 2 common techniques, the 2 that are like by vast margins the most popular ones, the ones that we need to cover in a compression course, are called arithmetic coding and Huffman coding. We're going to do Huffman coding first. We're going to come back and do arithmetic coding, and that factors into our later study of prediction. We're going to come back and do that, I think, in late June. So if we go back to our just the example with the cars, let's take a look at this. This is still a different example from earlier, so notice that our probabilities aren't as skewed as before, but they don't come out to have information contents that are whole numbers. If we go back to our example of watching cars on the highway, we have this sequence. So I've got a first order entropy of 1.97 bits. And there are 20 symbols in the sequence. So if I use a 2-bit encoding, it comes out to be 40 bits. My lower bound is 39.42 bits. Could I conclude, therefore, that in this sequence, if I use a 2-bit encoding, we'll just come up with an obvious one. If I use this, then I guess with my 40 bits, I am achieving the lower bound. It is true that if this is the entropy, the lower bound would be 20 times 1.97, which turns out to equal 39.42. So I am achieving the lower bound. Does that mean that I have achieved optimal compression? Well, I mean, I could then ask the question, can I represent the sequence in 10 bits? But if I have optimal compression, 40 bits, then the answer should be no, right? Well, that lower bound, again, is based on an assumption. And the assumption is one that we're going to spend a lot of time fighting with, and that is that the sequence is independent and identically distributed, but that tends to be less of a problem if we can ensure independence, at least in our context. And we could then ask, but isn't the sequence independent? Here are the probabilities. There is something a little bit suspicious about these probabilities. A little bit suspicious. Although these information contents and probabilities aren't inherently bad, there is something weird going on here. And it turns out that the assumption doesn't hold. Let's look at the gray cars. Here's a gray car. Oh, it comes after a red. That's weird. Here's a gray car. It also comes after a red. here's another one, but they all come after a red. This sequence of data is not independent at all. It turns out that gray cars only appear after red cars. Every single occurrence of a gray car is after red. And moreover, every red precedes a gray. So this is not a sequence of independent symbols as far as we're concerned. This particular sequence doesn't demonstrate independence because we have a clear dependence. And it turns out there's a second dependence, which is blue and purple. So every single blue car occurs right after a purple car. And really, not only does that tell us that we don't have independence, and that means that although we can still measure the information content of a symbol, our lower bounds no longer applies. We no longer actually have independence, so the bounds that we're deriving are bounds based on entropy, no longer make any sense, and therefore maybe it is possible to encode this sequence in 10 bits. So that bound doesn't apply, and in fact, I could stare at this and realize that actually if red is always followed by gray and purple is always followed by blue, for all I know, what I'm looking at is that every purple car on the highway is towing a blue car behind it, and every red car is towing a gray car. So really, I don't actually have red and gray cars. I've got red, gray, and purple, blue. So I can create a new set of symbols, purple, blue, and red, gray. Now, I now have a sequence of 10 symbols. Each symbol is twice as long, I guess. I mean, it contains twice as many details about reality as what I had before, but by batching these symbols together to make two symbols into one, I have eliminated some of that dependence. So now what I have is the purple-blue symbol occurs with probability 0.4 and has information 1.32. The red-gray symbol has information 0.74. The total entropy of this sequence, interestingly, is less than 1 bit per symbol, 0.97 bits, and the lower bound is 9.71 bits. So indeed, I might be able to find a way of representing the whole sequence using 10 bits. Let's see if we can come up with one. How about this? I'll use a 0 to represent the purple-blue car and a 1 to represent red-gray. So that means we've got 1, 1, 1, 0, 1, 0, 1, 1, 0, 0. Okay, there's 10 bits. Now, you should look at this and say, okay, as far as a compression scheme, we're definitely not done yet. How do I tell the decompressor about what symbol means what? That's a fair point. That is something we're going to have to unpack in the next 2 lectures as we discuss the subject of how to actually create these encodings. But certainly that's a relevant point. What we care about for now is, even if I come up with a clever encoding and the decompressor somehow knows it, how many bits can I expect this to take? That's what we're talking about in this lecture. So, okay, the slide also thinks that's a good encoding. We just use a 1-bit encoding. Then we can encode the entire sequence into 10 bits. Now, this sequence here also exhibits some dependence, but not the same level. And I want to use this example as a way of showing that even if you don't have the dead obvious dependence that we had here, you still have dependencies, and that still means your lower bound doesn't apply. So in this case, if we take a look at our gray and purple or our gray and blue cars, notice that there are red cars that are not followed by gray. So here's a red followed by a red, and then over here we've got a red followed by a purple. However, every gray car is still coming right after red. There is no gray car off by itself without a red coming before it. And similarly, every blue car is still right after a purple, which means there is still visible dependence. And I should be even more clear and say, even if there are some blues living by themselves, if a lot of blues occur after purples, an unreasonable number, that could still mean there's a dependence, just not a dependence that's universal. So dependencies can exist in lots of ways, and in fact, it can apply in ways that aren't necessarily obvious. So we can even observe in some cases dependencies like this. Notice that we've got a purple followed a few cars later, so 3 cars after a purple, we had a gray. And here, 3 cars after a purple, we have a gray. And if that happens a lot, there could be dependencies that span several symbols. I could have a dependency that starts in one place in my sequence and affects something that happens way later on. They don't have to be next to each other for a dependency to exist. And that's why it's really hard to really know that you have no dependencies. You can't just look at pairs of symbols. You have to consider every possible combination of symbols, every combination of 2 symbols, even if they're far apart, but also every combination of 3 symbols. So it could be that if you have a green followed 4 later by a blue, then for some reason, it's very likely that followed 5 after that, you're going to see a red. You can have symbols, dependencies that are formed by huge groups of symbols distributed widely over your sequence. So if you look at actual data, the statement, "this is independent," is actually very hard to make. So in this sequence, there are some dependencies, even though they're not universal. They're sort of one-way dependencies. Every blue is after a purple, but not every purple comes before a blue. And every gray is after a red, but not vice versa. So there is still some dependence visible, and that means that our lower bound doesn't apply. The entropy in this form is apparently 1.81 bits, and the lower bound is 36.3 instead of 40 if we use a 2-bit encoding, but that we shouldn't really read that to mean anything because we know that there's dependency. I have a few ways of removing it. So in this case, what I could do is still package together symbols. I could say, you know what? There's no such thing as a blue car. There is a purple car with a blue car that it's towing behind it. There are still purple cars. So if purple cars are tow trucks, then I guess there's a tow truck with nothing attached to it. So purple can exist on its own, but there's no such thing as a blue. So what I could do is make two kinds of purple symbol. I could make purple by itself and purple plus blue. I could make red by itself and red plus gray. And then whenever I saw the red-gray pair, I encode that as a separate symbol from a red that's on its own. If I do this, and I believe that I've now eliminated my dependencies, and remember that even if I remove obvious dependencies, there could still be less obvious dependencies. But the more that I eliminate, the closer I am to being able to trust that lower bound. I can use that lower bound whenever I want. The problem is the lower bound is sort of lying to me if there are dependencies. But the more dependencies I remove, the closer that lower bound is to being realistic. And that's good because that means the better I can expect entropy coding techniques to work. So removing dependencies is important if you have actual data and you want to use entropy coding. So if I do this, the resulting entropy of my sequence is actually 1.88. In the previous version, it was 1.81. So I changed the encoding of the sequence to change the symbol set, and the entropy went up, which is sort of weird. But if you think about it, because I have some symbols that are compound that tell me about two different cars at once, I suppose it makes some sense that if I look at my next observation, maybe there is more information in that on average, because I could hear about two cars at once if I wait for one more observation. So my entropy gets higher. But since the sequence is shorter, because there are now fewer symbols, because I batched some of them together, the lower bound is now lower. It's 24.5 instead of 36.3. And so if magically I can think of some encoding that realizes that, then I can expect I can achieve a 24.5-bit encoding on average, so let's say 25 bits. And so we now have this problem of, wait a minute, if I've talked about this lower bound and optimal compression, and I begin talking about entropy being the average number of bits, so the entropy is the average number of bits for one symbol. If entropy is the average number of bits in the best encoding, how can I do that if then I can, manipulate my data, combine symbols together to achieve some better encoding? And the key thing is, it's because I'm leveraging patterns. If there are patterns in the data, then the entropy bound doesn't apply. It isn't the best encoding if there are patterns that aren't being accounted for. So that's, again, a key distinction to make. And I want to just double back on that a little bit. So remember that I've called H of S the first order entropy, and that assumes that every single symbol is independent from all previous or future ones. There are no patterns. There are just random chances, because really entropy is designed as this measurement of sampling a single random variable that generates a symbol, I guess, that has an outcome. I could define higher order entropies that account for dependencies. So I could define second order entropy, which accounts for patterns between pairs of symbols. So if I notice, for example, in my sequence of symbols that I often see A, B together. Well, first order entropy only considers the probability of a single symbol occurring, without a reliance on its context. Second order entropy is computed based not only on the probability of one symbol occurring, but on the probability of various two symbol things occurring. Two symbol pairs in a row, two symbols that are separated by 1, two symbols that are separated by 4 or whatever, or 5. So second order entropy incorporates dependencies between various pairs of symbols. Third order entropy incorporates dependencies between 3 symbols, no matter how they're distributed. So 3 symbols separated by some amount. Notice that there is a dependency between A and itself in this sequence. A seems to occur 3 characters after the previous A a lot. And that's a dependency that would only necessarily be captured, I guess in this case, by second order entropy, or in some cases by third order entropy. And I can keep going further and further. And so I can therefore adapt that to describe what we could call the true entropy of a sequence. The true entropy is a version of entropy that incorporates all possible dependencies between characters. Now, for a sequence of arbitrary length, that is something that you can't compute because it requires a limit that goes to infinity, but we can understand, though, that because dependencies of more than n characters can't exist if I have a sequence of length n, if my sequence has length n, there can't be dependencies between n plus 1 characters. So in a sequence of length n, the true entropy of the sequence, h infinity of s, will just be equal to hn of s. Or maybe I should write that as h of the length of the sequence. So it is a computable quantity, but it's incredibly difficult to compute. So I basically have to consider every possible selection of symbols from inside the sequence. So I have a sequence of length n, keeping in mind that for a compression scheme that could be hundreds of kilobytes or a gigabyte. I have a sequence of length n to compute the true entropy and discover all the dependencies, at least as far as a naive computation goes. I have to consider all possible ways to select a subset of n things. And of course, we know that there are 2 to the n ways of doing that. That's exponential. I'd really rather not have to run an exponential time algorithm on an input of any size, frankly, but certainly not of size, I don't know, like 10 gigabytes or 1 gigabyte or 1 megabyte, if I can avoid it. So because true entropy is very difficult to compute, and also because just because I can compute the true entropy doesn't necessarily mean I have an easy way of encoding my symbols. It just tells me what the lower bound is. Because true entropy is very difficult to compute and not very practical even if I have it computed as far as getting anything done, we don't want to use it. So instead, if we want to leverage the benefits of this entropy bound, what we're going to do is try our very best to make first order entropy relevant. And the way we'll do that is take our data and do everything possible to wring out all possible dependencies. If our data has no dependencies between symbols, then first order entropy is meaningful. So instead of worrying about higher order entropy, we will just do our best to transform our sequence of symbols into something that doesn't have dependencies, where we can then use first order entropy. If you want to know more about higher order entropy, because it's not very nice to you if I now spend 2 hours talking about that during this lecture. If you want to know more about it, read this. This is a great book for the theoretical aspects of compression. So take a look at that. It's a book you can get for free if you're in this course, so just go do that. And as I said, if you're a grad student and you want a presentation topic, this is a great one. Higher order entropy is really interesting, and discussions of how it can be computed and what you can do when you have it, I think are really interesting. So we have all these sequences that we might be working with, and these aren't even real data. These are this hypothetical thought experiment of watching cars on a highway. And we notice if it contains dependencies, it's very hard to discover all of them. We can discover some of them, but not all of them. And we know that the more dependencies exist, the less relevant first order entropy is. We can still use it as a rule of thumb, but it's not very relevant if there's lots of dependency in our data. And so in this case, because of the obvious dependencies, if we use the bound based on first order entropy or techniques that rely on entropy coding, we may not get the optimal compression that we want so badly. This new sequence has less dependency, even if it still has some, so first order entropy is more relevant. As I said, maybe we can't even discover all the patterns, but the more patterns we discover and remove, the more independent we make each symbol from the remainder of symbols, the more likely that entropy coding techniques will actually be optimal, will produce optimal compression. And so rather than worrying about higher order entropy, we will just apply entropy coding to sequences that we've already worked on with other techniques that hopefully eliminate patterns in the data, remove dependencies. And this is something that large compression schemes also do. So we're going to study a lot of techniques, gzip and bzip. It says several, but really we're going to do gzip and bzip in detail. And most of those formats use a pretty common pattern. Entropy coding is really powerful. And so these formats want to use entropy coding. But first, they have to eliminate dependencies because entropy coding doesn't work very well. It doesn't get traction on sequences full of dependencies. So these schemes usually follow a path like this. They first use techniques that identify various patterns and then apply transformations to produce a new sequence of symbols with less dependencies. So that would mean something like what LZW does. LZW would, let's recreate our LZW example here, our stock LZW example. Symbol 257 in the LZW examples from a previous lecture was a replacement for a recurrence of AN. And we know that, if we see AN 2 times in the sequence, well, that's going to be we can see that there's some correlation. And if we compress lots of English text containing the word banana, then we're probably going to see AN over and over again. That's a dependency. Entropy coding is less effective on sequences full of things like that. If, on the other hand, we eliminate the dependency, for example, by creating new symbols and over time creating more and more symbols to turn patterns into symbols, to condense them down, we have less dependencies in our data. It's true that we might eventually see AN257 again, but that's a bit less dependent than AN. So these schemes will apply transformations that produce a new sequence of symbols, even if it's longer. And the new sequence will have less dependencies. Once we have a sequence that's hopefully fairly independent, we then hit it with some entropy coding scheme, like arithmetic coding or Huffman coding. As it happens, both gzip and bzip use Huffman coding. There are a variety of reasons for that, one of which is that arithmetic coding historically was seen as being rather slow. And with the resources available for compression and decompression in the 90s, I guess it was eventually decided that it was better to just use Huffman coding, which also has very nice performance. Arithmetic coding is used a lot more in more modern schemes. It's actually available in lots of schemes that may or may not use it. So historically, JPEG provided arithmetic coding as an option, but generally speaking, JPEGs use Huffman coding. And more advanced formats like LZMA do leverage arithmetic coding. For gzip, which is a scheme called deflate, we see that in the following way. So we see that gzip will first divide the input data, so a big input file, into blocks of a manageable size, bounded above by a constant. We know that by bounding our block size by a constant, we are allowed to look at a bunch of data at once without violating the streaming requirement. Gzip does this in a clever way, or it's allowed to do it in a clever way. The compressor has wide latitude to make decisions. Gzip compressors can choose the block size cleverly if they notice that patterns seem to fall along certain boundaries. So if gzip is working inside of a file where a certain part of the file has one pattern and the next part has another, gzip is allowed to decide that that the blocks will be chosen so that each piece of the file ends up with a different block, so it can compress each piece separately. Now, the extent to which it actually does that varies depending on the compressor, but gzip chooses the block size based on a variety of different factors, including the characteristics of the data. It could even look at the block and decide, is this data likely to be compressible? If it looks like random noise, let's just put it aside and compress it with a different technique, or not compress it at all to avoid expansion. Then, once it has blocks, it translates our 8-bit input symbols into 9-bit symbols. There are those 9-bit symbols again. And the 9-bit symbols also have interspersed with them a bunch of arbitrary binary data that represents offsets. Now, we'll come back to that later at great length. It uses a scheme called LZSS, which is a member of the LZ family of schemes, to prune out duplicated patterns, so to remove some of the redundancy in the data. When it's done, there is this sequence of 9-bit symbols, and then it constructs a Huffman code based on those. The idea being that the sequence of 9-bit symbols hopefully has more independence than the sequence of 8-bit input values. Now, actually, this slide is really oversimplifying things. This step of constructing a Huffman code is way longer than it looks. We just don't know anything about Huffman coding yet. When we get to assignment 2, your nightmare on assignment 2 will be happening sort of in this area. So have fun. For bzip, bzip, as I've mentioned before, is a highly pipelined scheme. It uses the following process. First, it applies a particular form of RLE. You may recall that is the version where we encode runs only after we've seen 4 occurrences of the same character. So if I see 4 A's in a row, then I might write the number 5 to indicate that the run has length 5 after the 4 A's. Or the number 0 if there are no more A's afterwards. But I only encode a run length if I've already seen 4 of the same character. That's the first stage of bzip 2. Then we apply something called a BWT, a Burrows-Wheeler transform. A Burrows-Wheeler transform is not a compression technique in itself. It takes a sequence of n symbols and creates a sequence of n symbols over the same alphabet. It just rearranges the input. But it does it in an incredibly clever, like a deviously clever way. I think the BWT is as close to magic as we're going to see in this course. It's not magic, but it is really clever. Like, to think about the inventors of that scheme, what they were thinking of when they came up with it, they were very clever. The BWT rearranges the symbols in a certain way that makes compression much easier. Then bzip applies a move to front transform. And again, move to front, I shouldn't even call this coding. I should call this a transform. Although this is closer to coding because move to front generates indices, not just the same set of symbols rearranged. So I apply a move to front transform to the output of the BWT. It turns out, as we'll see when we talk about Burrows-Wheeler transforms, that move to front, that Burrows-Wheeler transforms produce data in a characteristic form that move to front can often make a lot of progress on. Once I've done that, once I've applied these two transformations in a row, keeping in mind that neither of these are compression techniques themselves, I then use RLE again on the output of the move to front transform. And we'll see that this is also a very deviously clever trick because the output of the move to front transform has a very predictable way that it generates runs of consecutive characters. And once that's done, I construct a Huffman code. Like with deflate, this stage will end up increasing the number of symbols because extra symbols have to be introduced to accommodate things like run links, the metadata associated with run links. And so when I'm done with that, I construct a Huffman code based on the new set of symbols, which hopefully is independent or more independent than the input, and then encode the data using that. And I'll add that, strangely, this first RLE stage, in the eyes of the bzip designer, is actually superfluous. This was added for reasons that had nothing to do with achieving compression. It was because of an issue with the sorting algorithm, with quicksort, that was used in the Burrows-Wheeler transform. We'll come back. I'll complain quite a bit about that in a later lecture. And so also worth noting that we'll come back to when we talk about bzip is that, strangely, before the entropy coding, which now we should understand is sort of a standard last stage of the process to squeeze the last few bits out of a sequence that we've already eliminated patterns from, other than the entropy coding, the only real compression technique applied by bzip is RLE. bzip is just able to supercharge RLE by applying these transformations that boost RLE's performance. I think it's pretty clever because if you consider the compression technique used by deflate, which is LZSS, it's quite a bit more complicated than RLE. And you'll notice that, I think, definitely in assignment 2. And yet, bzip does tend to perform better than deflate on many inputs, on a large number. In the previous lecture, bzip just went to town on that topography data. So that's something to keep in mind. Now, the next 2 lectures, we're going to spend talking about one form of entropy coding, so generally speaking, something called prefix coding, which is the idea of finding a clever way of encoding a bunch of different symbols where I use a different number of bits per symbol. So I might do something like this. This might be 110, this would be 101, and then this could be 111. I might want to use a different number of bits to encode each symbol because I want to fairly value them. We'll talk about that with the separate encoding idea in the next 2 lectures, and then we'll pivot and talk a bit about deflate. And we'll come back later to talk about arithmetic coding, which doesn't represent each symbol with a separate sequence of bits.